Hi everybody, I hope this video finds you well. In today's video, we're going to be finishing up our work with the descriptive statistics of quantitative variables. So far, we've made quite a bit of progress working with quantitative variables. We've learned the three basic attributes that we want to measure about quantitative variables, namely the center, the variability, and the shape or distribution. Along the way, we've learned two measures of center, the mean or average and the median. We've also learned three measures of variability, the range, the standard deviation, and the interquartile range. We learned a nice summary that to be able to give for quantitative data, which is called the 5-number summary and consists of the minimum, the first quartile, the median, the third quartile, and the maximum. And we've also seen two ways of visually displaying quantitative information, which is not only sort of a nice way to help somebody sort of see and understand the data, but it also helps us measure the shape of a quantitative data set. And those two visual displays were the histogram and the stem plot. In this video, we've got a couple last things to wrap up. One is that we'd like to talk about one last basic visual display of quantitative data, which is called the box plot, and we'll get to that in just a moment. And the second is that we'd like to talk a little bit about why we have been using or sort of practicing this interquartile range. And this is actually going to tie back to something we discussed way back at the beginning of introducing our work with quantitative data. We talked a little bit about extreme values. This was actually when we were discussing measures of center initially. We sort of introduced the concept of a resistant measure versus a non-resistant measure. Remember, mean is a non-resistant measure, while as median is a resistant measure. And we've actually talked about resistance for things like the range and standard deviation also both being non-resistant, and the interquartile range being resistant. And we said that you had to be sort of careful using non-resistant measures whenever you have extreme values. But we didn't really say too much about what sort of counts or how do we classify a value as potentially extreme. So we're also going to discuss in this video how to use the interquartile range, the IQR, to actually diagnose if there are extreme values in our data set. So we've got a couple of different odds and ends to sort of tack on to finish up the quantitative variables, and after we do that, we'll get to see an example, summarize this, and then we'll be all done with the descriptive statistics of quantitative data. So let's go ahead and get started. So the first thing we're going to talk about is what's called the IQR Outlier Check. So let's start with a definition. An outlier is simply a data point that is far away from the general pattern of the data set. In other words, an outlier is an extreme value. So instead of constantly saying extreme value or something like that, we're going to use sort of the fancier term outlier. So our question is, how do you sort of diagnose if there are outliers in your data set? Say you have a bunch of data points that are in the hundreds and you have a data point that is 10,000. I think we could all agree that that's going to be an outlier. If you have a bunch of data points in the hundreds and you have a data point that's 200, it might be a little bit harder to tell, does that really classify as extreme? So we're going to use the IQR for a process for checking if there are outliers in our data set. You might ask yourself, why do we choose the IQR as a way of doing this? Well, remember, the IQR is resistant, which means that it won't be greatly impacted if there are extreme values, which is great, right? Because if you're using something to sort of see if there are extreme values, you don't want that same thing to be sensitive to extreme values. So we're using something that, even if there are extreme values, won't get too sort of messed up or affected by those extreme values. So it's the perfect thing to use to check for them. So the IQR Outlier Check is a two-step process for checking for outliers. Step one is where we construct lower and upper bounds for our data set. And basically these lower and upper bounds sort of give us a range for what we consider typical values in our data set. In other words, a range for what we consider not extreme. So we construct the lower bound by taking the first quartile and subtracting 1.5 times the IQR. We construct an upper bound by taking the third quartile and adding 1.5 times the IQR. So in other words, we go lower than the first quartile and higher than the third quartile, and that gives us a range for what we think is typical. Then step two says that any data point that is lower than this lower bound or higher than the upper bound are considered outliers. In other words, any data point outside this range that we construct from the lower bound to the upper bound is considered an outlier. Now, a couple quick notes here. You might ask yourself, why do we use 1.5? Well, 1.5 is our first example in this class of what is called a statistical convention. There's no real deep reason why 1.5 is used. You could argue for a different value, but in statistics, most statisticians have agreed that 1.5 is a good choice for the value to use here. So it's the one that we'll be using, and it is what is called a statistical convention. Just something people have agreed upon is sort of the right choice there. The other note that I'd like to make here is that while we will see some examples of using this outlier check, just because you're checking for outliers doesn't mean that there are outliers. So as a note here, it is certainly possible for a data set to have no outliers. And in fact, a lot of data sets that we look at won't have any outliers. But this is the process here to check if there are any. Okay, perfect. So this gives us sort of our first little extra addition here. We've been using and calculating the IQR a lot in the last couple of videos, but we haven't really seen why it's necessary, and now we sort of see why that is, right? It's going to be used to check for outliers. All right, before we get to an example, let's go ahead and also talk about that other visual display, the box plot. So let's have a little discussion about that. So this is our third visual display of quantitative data. Remember, we've talked about the histogram, we've talked about the stem or stem and leaf plot. Now we're ready to talk about what's called a box plot. So a box plot, again, is a visual display of quantitative information, but it's a visual display based on that 5-number summary. So the box plot and the 5-number summary sort of go hand in hand. To draw a box plot, we first construct a horizontal axis. So we'll draw a horizontal axis and we'll label it using, a consistent scale that matches whatever the values of our variable is. Then we draw a box, and that box is going to start at Q1 and end at Q3. So your box is going to extend from the first quartile, whatever the value of the first quartile is, to whatever the value of the third quartile is. Inside of the box, we're going to draw a line at the median. So there's going to be a box that goes from Q1 to Q3, and then a line somewhere in between at the median. Finally, we extend lines from the box to the minimum and maximum values of the data set. So notice that the 5 sort of things that you need to draw a box plot are the 5 numbers in the 5-number summary. So, a 5-number summary is nice, but how does it help us sort of achieve our goal, which is to understand the shape or distribution? Well, unfortunately, a box plot is a little bit more limited than a stem and leaf plot or a histogram. A box plot can only distinguish between right-skewed, left-skewed, and symmetric, meaning you can still tell if something is right-skewed, you can tell if something is left-skewed, and you can tell if something is symmetric. Unfortunately, in the situation where the box plot tells you it's symmetric, you're not sure if that symmetric distribution is Bell normal or uniform. You just can't make that sort of call using a box plot. So how do we decide between right-skewed, left-skewed, and symmetric for box plots? Well, we can sort of see in the following situations. A right-skewed box plot is going to look something like this, where if this is your Q1, this is your median, and this is Q3, that the distance between Q1 and the median is much smaller than the distance between the median and Q3. So if you see a box in a box plot that looks like that, that tells you that you're looking at a right-skewed distribution. Left-skewed, as you would expect, sort of is the opposite. It means that you get a box that looks like this, where this, again, this would be Q1, this would be our median, this would be Q3. So the distance between Q1 and the median the distance between the median and Q3, well, the distance here is going to be much larger than the distance there. And symmetric, as you would expect, is where that median sort of falls right in the middle, or at least roughly so. So again, that would be Q1, that would be the median, that would be Q3, and the distance between the first quartile and the median and the third quartile are the same. As a side note here, notice that when looking at a box plot and analyzing the shape, the lines that we'll be drawing when we actually draw a box plot that'll extend out to like the maximum or out to the minimum, those are not used for distinguishing the shape. As a side note, sometimes those lines out to the side are called whiskers. Some people reference these as box and whisker plots. But the reason that we don't use those sort of lines out to the minimum and maximum is because those are determined by only single values, right? The line out to the minimum is determined only by the minimum value in your data set, and the line out to the maximum is entirely determined by the maximum value in your data set. So individual data points shouldn't determine the overall shape of your distribution. I mean, if you just think about an extreme case, you might have thousands of data points. You wouldn't use one of them to just say what the shape is. So when we're talking about the shape, you just use the box component of the box plot. Okay, so at this point, we've introduced why the IQR is actually useful from our perspective for finding outliers, and our third and final visual display. Let's go ahead and take a look at an example that'll put all this stuff sort of together. So, for our example here, let's suppose that we have a researcher that's interested in studying the weights of patients that come to a healthcare clinic. So, to study this, the researcher randomly selects 15 recent patients from the clinic and records their weights in pounds. So they get the following data. So there was somebody who weighed 12 pounds, somebody 97, somebody 173, all the way up to 248. So we're going to do most of our standard things: identify the population sample and individual, identify the sampling technique, calculate the mean and standard deviation, give the 5-number summary, then we'll draw the box plot. We'll use this to describe the shape, and then we'll talk about, are there any outliers in this data set. Now, before we get to discussing outliers, let's think about which of these data points even has the potential to be an outlier. If we look at this data set, are there any values that seem really extreme? Well, this 12 certainly seems much lower than everything else, and this 248 does seem a good bit higher. So we would anticipate that if there are any outliers in this data set, the 12 has the best chance of being an outlier, and maybe the 248. But if the 12 isn't an outlier, then the 248 is not an outlier, because the 248 is definitely much closer to the rest of the data than the 12 is. Notice what I'm trying to get you guys to sort of think about here is that in a data set, you might find one, maybe two outliers. You're not expecting that there's going to be dozens of outliers when you only have 15 data points. And certainly there's the potential that none of these are actually outliers. So we need that outlier check to make that decision. All right, though, let's go ahead and get started piece by piece here. So we'll talk about the population, the sample, and the individual. Well, our sample should be those 15 patients that we're studying, so 15 patients. The individual then, of course, would be one patient, and I guess the population would be all patients at this clinic, or of this clinic, however you want to phrase that. So once again, same structure, all a certain amount, and one of whatever the individual is that we're looking at here. And in this case, I think we'd classify them as patients. All right, what about the technique here? Well, if we go take a look at this, it says that we did randomly select the 15 patients, so that means we're looking at something that is either an SRS, stratified, or cluster. Notice we're not given any other information about how the researcher made these selections. We just know that it was done randomly. So that means that the technique that was used here should be an SRS. We didn't get any other information. They didn't make sure to take, some patients that maybe had, were male and some patients that were female or anything like that. That would be stratification. It's just an SRS in this situation. All right, let's go ahead and get our mean and standard deviation. Of course, it is a sample, so we'll use that notation there. So, of course, we'll use our calculator for this. So let's go ahead and get that data typed in. So you can hit stat and edit, and then get in at 12, 97, 113, 126, 143, 164, 168, 173, 179, 185, 195, 198, 203, 212, and 248. Once we have all that in there, you should have 15 data points. Then you can hit stat, calc, and 1var stats, and we can get our information there. So it looks like our X bar should be approximately 161.1 after rounding, and that would be in pounds because all the weights were in pounds. And the standard deviation looks like it would come in at about 57.1 pounds. And of course, again, we would use the sample standard deviation because this is only a sample. All right, let's go ahead and get that 5-number summary. So our 5-number summary here. So that means we want our minimum, Q1, the median, Q3, and the maximum. Again, we could easily do that by hand by just looking back at our data, but we can also just grab it from the calculator. The minimum was 12, Q1 was 126, the median was 173, the Q3 was 198, and the maximum was 248. And of course, all those would be in pounds. Now, since we are coming to sort of the end of our discussion about quantitative data, at least for now in terms of the descriptive statistics, let's just go take a quick look about this 5-number summary and make sure that, what the calculator is sort of telling us really does make sense. So if we look back up here, obviously, it's very clear that the minimum was 12 and the maximum was 248. This is telling us that the median was 173. So let's see if that makes sense. 173 is right there. Let's see, there's 1, 2, 3, 4, 5, 6, 7 things there. 1, 2, 3, 4, 5, 6, 7 things there. So an equal amount of data less than the median and an equal amount of data greater than the median. Remember, that's what the median is supposed to do. It's supposed to cut your data directly in half, so that makes sense. Then, if we think about this Q1, 126, that would be located right there. Notice that that cuts it into 3 and 3 there. And then, of course, the Q3, 198, that would be located right there. And notice that the quartiles really do cut it into 4 equal pieces. 3 data points, 3 data points, 3 data points, and 3 data points. So, again, this is just sort of confirming that what the calculator sort of spits out for us is indeed correct there. All right, so we now have our 5-number summary. Let's go ahead and draw a box plot from this data set. So let's actually use this now. I'll do this right here so we can reference it. So how do we begin to draw a box plot? Well, first thing we want is we want to draw a horizontal axis. Then we need an appropriate scale. We have to basically go from 12 all the way up to 248. So I might just start at, say, 0 and go by like 20s. So there's 20, 40, 60, 80, 100, 120, 140, 160, 180, 200, 220, 240, and I'll have to go a little bit further, 260. And of course you want to label this, so this would be weight in pounds. Okay. So there's our axis. So whenever you're starting a box plot, you need to start an axis there. You can pick any scale you like as long as you have a consistent scale. So we now need to locate Q1 and Q3. So Q1 is 126, so it should be just a little past 120. So we'll start our box there. And Q3 is 198, so that's going to be just a little bit before 200. So right about there. And then we'll draw in our box there. So that's the box component. Now somewhere in between we can go ahead and we can find the median, which is 173. So 173 looks like it should be maybe right about there. Okay. And then that completes the box component. Now we just need to put lines out to the minimum and maximum. For the minimum, we would extend this line out to 12, which would be about there. And for the maximum, we'd extend out to 248, which would be maybe somewhere right about there. So there is our box plot. What shape are we seeing there? Well, we'd focus on this right here. Notice that the left-hand side is much larger than the right-hand side. If you want to check that, you can measure 173 to 126 and 198 to 173 by subtraction. If we subtract 173 minus 126, you can see the distance between these guys is 47, whereas the distance between 198 and 173, if you do that, is 25 only. So that means this is much smaller than this. So this is a larger portion. The larger portion is on the left-hand side. So we'd say that this is approximately left skewed. So our claim for the shape based on our box plot here is left skewed. Does that make sense based on our mean and median? Well, keep in mind that in a left skewed distribution, the mean is supposed to be less than the median. Our mean was 161 and our median was 173. So that does seem to make sense because our mean is a bit lower than our median here. Alrighty, now let's go ahead and finish this up on another page for the outliers for this data set. So before we do that, I am going to grab this 5-number summary here because we will need that. So let's just copy that and we'll give ourselves a fresh page so we can reference our data. So there is part D there, and we'll go ahead and do part F now. So are there any outliers in this data set? So first thing we need to do is we need to get the IQR. IQR is Q3 minus Q1. And of course, that's 198 minus 126. So 198 minus 126. Looks like that should come out as 72 there. So we now have our IQR. Now, step one of our process here is we need to get our lower bound, which is Q1 minus 1.5 times the IQR. In this case, Q1 was 126 minus 1.5 times 72. You can type that into your calculator all at once, 126 minus 1.5 times 72. And if you do that, you should get 18. And for the upper bound, Q3 plus 1.5 times the IQR. So this time we use Q3, which is 198, and we add 1.5 times 72. Again, just type that directly into the calculator, 198 plus 1.5 times 72. You should get 306. So the lower bound is 18, the upper bound is 306. So now step two is deciding if there are any outliers. So if we look at our data set, were there any data points outside the range of 18 to 306? Well, 12 is lower than 18, so 12 would count as an outlier. 248, however, is inside this range of 18 to 306. So 248, not an outlier. So we would say that there's only one outlier. The patient who weighed 12 pounds. So we found out that that value of 12 is extreme enough, according to our method, to count as being an outlier. Now, a couple quick notes about this in terms of running this outlier check. First, make sure that when you go to actually do step two here, you always look back at your data. The only things that are potentially outliers are points from your data set. These bounds, 18 and 306, they're never going to be outliers. These are just made up values that we found to construct our range. The outliers themselves, if there are any, have to be in your original data set. Second thing to sort of keep in mind, why do we bother finding outliers? Well, the main idea here is that this person, this patient who weighed 12 pounds, is significantly different from everybody else. Now, there could be a couple explanations. You could imagine that maybe this is an error, right? Maybe somebody's typing in information and they really meant to type in 120. They type in 12 and the outlier check would catch that for you. Or perhaps this 12 is accurate. And in that case, this 12 probably represents a patient who's like an infant. Now, everybody else probably has more like adult weights, and that could basically tell a researcher that, yes, this 12 is accurate, but maybe that person, that infant, shouldn't be included in the original data set, right? I mean, we just happen to choose 15 patients, but if we've got 14 adults and one infant, maybe we should really separate those. Because if you think about it, yes, all those people are patients, but they're really different populations, right? Adult patients versus, child or infant patients. We might not want to lump them all together. So you can see why checking for outliers is important. One, just from a purely mathematical standpoint, it's important to know, are there any extreme values? Two, it could potentially help detect something that is a data entry error. Maybe this 12 is really supposed to be something else. Or, and third and finally, it can sometimes help identify members of a different population that somehow got put into your sample. Okay, so in this example, we've now gone back and reviewed one last time all the major descriptive statistics you need to be comfortable with: mean, standard deviation, 5-number summary. We've now seen the last visual display, the box plot, and how to do the shape of that, and we're able to detect outliers in our data set. All right, this pretty much wraps up everything we need to say for now for doing descriptive statistics with quantitative variables. In our next video, we'll be transitioning a little bit and spending some time focusing on a very particular type of distribution. We said back when we introduced shape and distribution that the normal or Bell distribution is one of the most important in statistics, and we're going to spend some time analyzing variables specifically that are normally distributed.